Assalamu alaikum. This is a brief overview of 7 common statistical tests with examples from the medical field. In this 1-hour presentation, we shall go through 7 common statistical tests with medical examples. We shall cover 4 non-parametric statistical tests, including the sign test, the Wilcoxon sign rank test, the Mann-Whitney test, and the chi-square test, followed by the t-test family, and these are for parametric data and the analysis of variance, and we end with correlation. Starting with the non-parametric tests, which are useful because they can be applied on any set of data, not necessarily normally distributed. They can be applied on data that are skewed or data that are kertotic. So it's distribution-free type of tests. They depend on the ranks of the data rather than its actual value. You'll have the very low ranks here starting from 1, 2, 3, 4 and so, and these will be the very high ranks, the highest and the one before and the one before. And working on the ranks, you could analyze the difference between the two groups. So whereas in a parametric test like the t-test, you compare the sum of the actual values or the average actual values in one group against the other. In a non-parametric test like a Mann-Whitney, you compare the sum of the ranks of a group against the sum of the ranks or the average ranks in one group against the average ranks on the other, and obviously this group has higher average than the other one.
The first example here, we are running a trial, for example, to see if there is a better way of doing tonsillectomy. So we had one tonsil removed by the standard technique and the other tonsil removed by the new technique in the same patient. And we had 9 patients enrolled for the study. And after 10 days or 2 weeks, we compare the healing between the two tonsils and we grade it, whether it is good or very good or excellent or moderate. So we end up with 2 sets of data, the tonsils that have been removed by the standard technique and the tonsils that have been removed by the new technique. Notice that the 2 sets are paired. Each patient had the 2 techniques, one with the standard and one with the new. With the standard technique for patient number 1, the results were good, but the results with the new technique were very good, so we put a positive sign here. In the second patient, both were good, so we put a 0. There is no difference. In the third patient, the result of the standard technique were better than the new technique, so we put a negative. And we go on with the 9 cases and end up having some who have a better healing with the new technique or no difference, or a better healing with the standard technique. Then we count up the number of the positives, it is 6, and the number of the negatives, it is 2, and the number who have equal, it is 0, will just be omitted. So the total number of patients are now 8 rather than 9 because we have deleted the results where there is no difference. And that's about it. Now we have 6 positives and 2 negatives, and the test statistic, the sign, is the lower of the 2. So the test statistic here, the S equal 2. And the number of the cases are 8. And what we need now is to check whether this small number is statistically significant or not. The difference between the 6 positives and the 2 negatives is statistically significant or not. Now, these 2 related sets of data can be observations on the same patient before or after a certain treatment, or it can be repeated measures on the same patients, or it can be 2 different tests carried out on the same patients, like examining a tumor by, for example, an ultrasound, or examining the size of the tumor in the second group by an MRI scan or pathology. Or it can be different observers, for example, grading the mark of students, observer number 1 and observer number 2, and we'll try to see the difference between the 2.
Start with an example. The Wilcoxon test would work on 2 paired data sets. 2 data sets that are paired or closely related. Like, for example, and post-operative recordings of, say, hearing, for example, weight, or any parameter that is examined before therapy and after therapy in the same individual, or repeated measurements of the same parameter in the same individual, like blood pressure measurements in the morning and the afternoon and the evening and so on, or two sets of data measuring the same thing by two different modalities, like if we are measuring a tumor size by two imaging modalities, an ultrasound and an MRI scan for the same tumor and the same individual, or two different observers marking tests, for example, for the same students. Each observer would mark the test differently according to his interpretation of the student's ability. So these sets of data are closely related, they are paired. These are the scores for the same individual by two different examiners. If we want to know if there is a significant difference between the way examiner A and examiner B mark their tests, we look into their figures with this, say, 10 different students. Indeed, there is a difference in the way they mark things. Sometimes examiner A would give a better mark than examiner B, and vice versa. In other situations, examiner B give marks more, and so on. It goes through the 10 different students. To find out if there is a significant difference, we would want to know how much of a difference for each individual student. So in student 1, there have been a difference of 7. In student 2, a difference of -3, because an examiner B has given a higher mark. And then in student 3, it's 3. And in student 4, it is -5, because again, examiner B had given a higher mark than examiner A. And we just go on through the 10 different students. Now, these differences are as small as 1, just 1, and is as big as 8, for example, in the last student. We start ranking these 10 differences from 1 to 10, starting with the smallest, ending with the largest. So the largest difference would take the rank of 10. The smallest, we have two different students with a difference of 1. So we give them both 1.5 rather than one of them would be 1 and the other would be 2. And we just go on from below upwards or from up downwards, but we rank these differences. And then we give these differences their respective signs. So if it is examiner A who has given the higher mark, it is positive. If it's examiner B who has given the higher mark, it's negative. Then we have 10 different scores here. We count all the positive scores separately, and then count all the negative scores separately, and try to find out the test statistic that is going to show if there is a significant difference or not. So now back to the example. We have done all the necessary calculations. We found the differences between the two examiners, and we have ranked these differences from 10 to 1, and we have given the ranks their respective signs, either negative if examiner B is given the higher mark, or positive if examiner A has given the higher mark. Now, we've added up all the positive ranks separately and all the negative ranks separately. And as we can see here, the sum of the negative ranks is 31 and the sum of the positive ranks is 24. Now, how can we find out the test statistic W? Simply, it is the smaller of the two rank sums. We just take the smaller, the 24, and that is the test statistic. The W here is the smaller of the two ranks. The Mann-Whitney is a good alternative to the more powerful parametric t-test. Say we are running a trial to find out the effect of a treatment on two groups. If the data is normally distributed, then we can calculate the mean of each group and its standard deviation, and then by the use of the mean, the standard deviation, and the number of patients in group A, and the mean and the standard deviation, the number of patients in group B, we can use the t-test. If the data is not normally distributed and we cannot calculate a meaningful mean, then we use the Mann-Whitney test. Here, the data would be ranked from
top to bottom or from bottom to top, and will depend on the ranks. Here, for example, the highest score was number 1. Will depend on the sum of the ranks in group A against the sum of the ranks in group B to find out if there is a real difference between the two groups after using the treatment. So the Mann-Whitney non-parametric test is based on ranks, not actual scores. You need to have at least 5 patients in each group. The data would be preferably continuous, but ordinal data can also be used. The samples are independent, the two groups are independent, different groups, and not necessarily equal in size. You could have 9 patients, for example, here and 12 patients on the other side. We'll go through 2 simple methods of calculating the Mann-Whitney U, the Mann-Whitney test statistic. Method number 1, say we are running a trial to compare the results of 2 different groups, a group of 4 females against a group of 5 males. These 2 groups are independent, different. And we are measuring either an enzyme or a hormone or a score of one sort or the other. And the way in method 1 to do it is to have these numbers in a table, 4 females on the y-axis and 5 males on the x-axis. This table will be a 4x5 table with 20 squares in it. And then we check each score of the female, number 1, against each of the male scores. So we can see that 20 is more than 19, then we mark it yes here. It's less, so we leave this vacant. It's more than 16, we put yes. Less, we keep it vacant. And then the second female, 11, would be less than all of the 5 males. The third female would be more than this score here, so we put yes. And the last female would be less than all the males, so we keep it vacant. So out of the 20 scores, the females scored more than the males in 3, and the males scored more in 17. We take the smaller, that's the 3, and that's it. That's the U test. So it's as simple as that. We just find out the number of the smaller of the 2 totals and this square, and that's the U that we are going to use it as a test statistic. The second method for calculating the U, which depends on the ranks of the scores. So we have here 4 scores for the females and the 5 scores for the males. We'd want to combine them into one set of scores arranged from the bottom to the top, or vice versa, it doesn't really matter. So the lowest score, which was 11, belonged to a female. This will be the start of the column, a female with an 11, followed by another female with a 12. The top score belonged to a male with a 29, followed by another male with 24. So we'd have the top 2 scores in here. So the 9 scores, the combined scores of the females and the males, are arranged from bottom to top in here, and then we rank them. We give the lowest score for a female is a 1. The second lowest was again a female, so that's number 2. The top score belonged to a male, that's number 9. That's the highest possible score rank. And just below that was another rank 8, belonged to a male, and so on. And then we take all the ranks for the female, that's number 1 and number 2 and number 4 and number 6, and add them separately. That will bring this sum of ranks for the females is 13, and do the same for the males. The sum of the ranks will be 32. So the sum of the 2 together is 45. These are the sum of all the possible ranks for the males and the females. That's the first step. And then we use the rank sum for the female, which was lower than that for the males, to calculate the Mann-Whitney test statistic, the U, according to this formula. The U is the rank sum for the females minus number of the females, which was 4, multiplied by the number of the females plus 1, which was 5, divided by 2. So this is the equation here. 13 was the sum of the ranks minus the multiplication of 4 times 5 divided by 2 is 10. So the final result, the U, is again the 3 that we have obtained by the first method. The U is actually signifies the degree of overlap between the two groups. The higher the U value, the closer the results to the null hypothesis. You would expect a null hypothesis to be true, that is to say no difference between the two groups, if the U approached in this example say a score of 10, for example, because this is what we expect if there is no difference at all. But with a score of 3 you would expect some difference, but that was not statistically significant.
The chi-square test is not just a single test. In fact, it's a family of different tests, the most common of which, of course, is the chi-square test for goodness of fit, or the independence test. There are at least 2 corrections for the chi-square test for goodness of fit that tends to make the results a little bit more conservative. These are the Yates correction and the Fisher's exact test. We'll go through these as well. And there is another version of the chi-squared called the McNemar's test, used if the data is paired or if you are using it to test inter-subject testing. And of course, chi-squared tests can be used to test for homogeneity in meta-analysis. And there is a non-parametric version of the chi-square test called the Goodman-Kruskal gamma test, used for ordinal data using ranking. So how does the chi-square test work? Let's take this example in which we want to check the gender mortality in a group of 30 patients with a certain disease. Those 30 patients were divided into 13 females and 17 males. 20 of them survived and 10 died. So the odds ratio for survival against death is 20 to 10, that's 2 to 1. If there is no differences between the genders in the odds ratio, if twice as much females survived against females who died, and the same applies to the male, then there is no much difference between the two groups. But if there is a difference between the two groups, like we see here, the observed difference is the odds ratio for survival for females were 33.33, that's 10 survived and 3 died, and for the males it's 1.43, that's 10 survived and 7 died. So there is an obvious difference. Now, chi-square tests would want to quantify this difference, and the way to quantify it is to find out imaginary figures, some expected figures that would fit this ratio 2 to 1 survived against dead in both genders. So the expected figures for females will be 8.7 against 4.3, this is 2 to 1, and for the males it will be 11.3 against 5.7, this is again 2 to 1, the expected ratio. The difference between these two figures, the expected and the actual, would represent the deviation of the actual count from the ideal situation. Then it would show that there is a difference between the two genders. How we calculate this difference? We subtract the two figures in the 4 squares. Some of them would be more and some of them would be less, some of them will be positive and some of them will be negative, and this would cancel each other, the differences. To avoid this, the differences will be squared in each of these squares, and then we take the sum of the squares that would represent the chi-square test, and if this sum is high enough, then there is a significant difference between males and females, and if it is less than a certain threshold, then there is no much difference. This is insignificant differences in the gender mortality. But there are certain rules that should be applied in a chi-square test. The total number of the values in the 4 squares should be at least 20. And the expected value in each of the 4 squares should not be less than 5. And in case we are using bigger tables like 3 by 3 or 3 by 4 or whatever, then only 20% of the cells should have a value less than 5, and none of these cells should have a value less than 1. The other thing is we need to measure the degrees of freedom for the chi-square test, because there are different curves for the probability distribution of the chi-square for different degrees of freedom. A degree of freedom of 1, which is by far the commonest, is a very skewed probability distribution curved. It normalizes as the degrees of freedom increases. How to measure degrees of freedom? It's the number of the rows minus 1 multiplied by the number of the columns minus 1. So that's 2 minus 1 equal 1, 2 minus 1 equal 1, so the degrees of freedom here is 1. If these rules are not fulfilled, the alternative is to use the Fisher's exact test. The correction introduced by Yates in the 2x2 tables would make the result of the chi-square a little bit more conservative. This is by subtracting half from the results of subtracting the observed against the expected from the expected, rather than just squaring this value. The actual modification is to subtract a half from this value, so this would produce, before squaring, so this would produce a more conservative x-square. You could see from this example that the chi-square result was 4.8, the value, after the correction it is 3.17. The 4.8 result was actually significant because it is 0.028, but after the Yates correction it became 0.07, which is non-significant. Another way of calculating the contingency 2x2 table is the Fisher's exact test, which can be used if any of the expected values in the 4 cells is less than 5, or if the rules of the chi-square test are not met, then the Fisher's exact test can be used. As you can see here, this is again a 2x2 type of table. The result of the chi-square for it was 4.8. and for the Yates correction it was more conservative at 3.17. When the Fisher's exact test was used, it's actually more here at 5.59, and this would give a different p-value for these 3 different values. It's significant here, it's not significant here, it's significant here. So it's important to know when exactly you should be using the chi-square or the Fisher's exact test or the Yates correction, because they can give different conclusions. And then a further member of the family is a McNemar's test, which should be used in a 2x2 table if the data are paired, like pre-treatment and post-treatment, for example. If the data are paired, pre-treatment, post-treatment, or taken from 2 observers for the same patient, or 2 measurements of a certain tumor by 2 different techniques, then rather than using the classic chi-square, the McNemar's test should be used. By far the most common application for the chi-square is the 2x2 tables, but of course you could also use it for multiple proportions, like if you have 4 different vaccines and you want to see its efficiency in, say, COVID, for example, whether patients have been infected or not, in the 4 groups. So it's a 4x2 type of table rather than 2x2. Now the difference here is that it would provide you with a different odds ratio in here, 4 different odds ratio. When you calculate the chi-square test here, the degrees of freedom would be 5 minus 1 equal 4 multiplied by 2 minus 1 equal 1, so you have 4 degrees of freedom, and the calculated chi-square would be 16 point something here, and this is significant. But which of these are different? What does it actually mean that the figures here are significantly different from each other? We look into the odds ratio here for the possibility of the effectiveness of these vaccines, and you could see that number C is probably the lowest of them, because most of them, the figures would be 0.15, 0.21, 0.18, 0.20, but this is 0.09. So we think that this is the odd one. This is what makes the chi-square test here show that there is significant differences between the vaccines. How to prove this? You simply take off the C from the table, so it becomes a 4 by 2 rather than a 5 by 2, and calculate the chi-square, and this time the value would be just 2.98, and the degrees of freedom here will be 3, and it would not be significant. So that would show that if you include the vaccine C, the results are significantly different from each other. If you take it out, the remaining 4 are not much different, so it is C which is the different vaccine. Now to parametric tests that should be used when the data is normally distributed, plus other things, of course, but the main proviso here is that the data are normally distributed. And the first test is the t-test, and again it's a family of different tests rather than just one test. We use this t-test when we want to compare a continuous result in two different categorical groups, like males and females, when we are measuring something continuous like weight or height or a blood hormone or an enzyme or something continuous in two categorical groups, or pre-treatment or post-treatment, things like this. So that's when we think about the t-test. The distribution of the data should be normal, and the variance of the data, the standard deviation of the data, the spread of the data in the two groups should not be too different. It should be quite similar to each other. If they are very different, like in here, spread of data here is different from this, then we use one member of the family, which is the Welch's test. So these are the conditions for using the t-test family. It can be used if we have only one sample, if we are comparing the result of the sample against a classic normal, or to compare results from two groups that they are not paired, or two groups that are paired like pre and post. And the fourth test, the Welch, is when the variance in the two groups is much different. And without getting into too much details, the value of the t and the t-test is basically the difference between the mean of the two groups. We just subtract the means of the two groups and divide this by a certain standardized figure. It's usually based on the standard deviation of the two groups, the pooled standard deviation, calculated by different formulas. But the idea is the difference between the means of the two groups divided by a certain figure derived from their standard deviation in order to standardize the difference of the means in terms of standard deviation. So the first member of the family is the one sample t-test, in which we compare results obtained from our sample against a known standard that we don't have to repeat in our study. We don't need to measure, for example, the temperature of controls, because we know that there is a known standard for the temperature of normal cases, or the blood pressure of normal cases, or any known standard. We can compare just one sample to that known standard, and that makes it more easy to calculate, because we'll be finding the difference between the mean of our group and the known standard and divided by the standard deviation of the sample we obtained, divided by the number of the sample. So this is the first member of the family. The second member is the paired t-test. The two groups that we are going to examine are paired. Each member of this group has another reading in the other group, or a corresponding reading in the other group, like a pre-operative and post-operative hormone level, or weight, or enzyme, or whatever. So there are two readings from the same patient. And here we find the difference between this pair of results. If we have 30 different patients in the two groups, then we find 30 different differences between the two groups, and we take the mean of the differences, and that would be the mean of the difference that is going to calculate the t-value through. And this will be divided again by the standard deviation of the differences between the two results in the same individual. So this would be the second member of the family. The third member is the student's t-test. This is by far the commonest of the t-tests used in statistics, in which the two groups are not paired. So we have two groups here, but we have variance of the two groups are not too different, and the distribution of the data is normal in the two groups. So we just measure the difference between the mean of group 1 and the mean of group 2 and divide it by a pooled standard deviation from the two groups to obtain the t-value. Now this is the student's t-test in action. We are running a study on the tumor size related to the incidence of puncture of pleomorphic adenoma related to its size. And as you would expect, when the tumor is very big, this is the size of the tumor, then the rate of puncture is higher than when the tumor is small. But we want to find out whether this is significantly different or not statistically. So you have two groups here, one with no puncture and one with puncture in the pleomorphic adenoma. In the no puncture group, they are much more, 156 patients. And the average diameter of the tumor was 31.9 millimeters. In the group of the punctured tumors, much less, 26 cases, but with larger tumors, as you would expect. The standard deviations are not very different, but the standard error is because of the differences in the numbers of the patient. Standard error would be the standard deviation divided by the square root of the numbers. In order to test whether the variance, the spread of the data in the two groups are similar or not, we use a test called Levene's test, which is, if significant, then there's no that the two groups variance are actually different, and we should not be using the t-test, we should be using the Welch test. But if it is not significant, like in here, then the variances are not too undifferent. And the results of the t-test showed that if we are using the student's t-test, this will be the result, 2.8, and it is significant. But even if we are using the Welch test, assuming that there was a significant difference in the variance between the two groups, it is still significant. And this is the Welch's test, the fourth member of the group that is used when there is unequal variance in the t-test. The spread of the data in these two groups are not equal. So this is when we use the Levene's test, and if it is significant, then we use the Welch test. The standard deviation by which we divide the difference between the two means is calculated from a certain formula, and also the degrees of freedom is calculated from a certain formula. It's only used, the Welch's test, when there is quite a marked difference between the distribution of the data in the two groups. And here is an example of using the Welch's test in a study to compare the safety margin of pleomorphic adenomas and the excise safety margin in two groups of patients, one who had recurrence and the other did not have a recurrence. So as you expect, where the safety margin is much higher in the group of the patients who don't have a recurrence, and it's much lower when in the group of the patients who had the recurrence. Those who don't have the recurrence, they have a safety margin of 5.99 millimeters, almost 6 millimeters, and those who have the recurrence have only a safety margin of 1.29. And of course, because the numbers and the two groups are different, the standard errors are quite different as well. So we run the Levene's test to check for the homogeneity of the variances of the two groups, and this time it is actually significant. So if it is significant, you cannot use the student's t-test, you should be using the Welch's test. And you could see from the result here that even if you use the student's test, it is still significant difference between the two, but you should be using the Welch's modification, and this showed a very significant test, a very significant result. When we compare results of two groups only, we can use a t-test or the non-parametric equivalent. But what if we have more than two groups at the same time, like 3 or 4 or even more? Then we need another type of tests to find out the differences, if there are differences between these 4 categorical groups. The outcome should be continuous. In this example, it is the tumor size in millimeters, and the level here could be 2, 3, 4, could be categorical, like this is superficial parotoidectomy, and this is revision parotoidectomy, and this is superficial parotoidectomy and total parotoidectomy. And these are the tumor sizes in the 4 operations, and we set up this study to see if there are statistical significant differences between the groups, which are more than just 2. So if we are in a situation that we need to compare results from 3 or more groups, in the usual 2 group scenario, if the data is parametric, we use the t-test. If the data is parametric and we have 3 or more groups, then we could use the ANOVA, one-way ANOVA. If the data is parametric and also paired or repeated measures in the same individual or a paired individual, then we use the paired t-test. If it's only 2 groups, if it is 3 or more, then we use a repeated measures ANOVA. There is a test equivalent to this with the ANOVA. If the data is non-parametric, 2 groups, we use the Mann-Whitney, but if it is 3 or more, we use the non-parametric version of the ANOVA, which is the Kruskal-Wallis test. If the variance between the groups is markedly different, like in here, when we're using the t-test for 2 groups, we use the Welch test, and here we also have a Welch ANOVA for data with different variances. So what's the idea behind this analysis of variance test? Simply, if we have 3 or more groups, like in here we have 4 groups, the differences between the 4 groups would be significant if we measure the variations between the groups and find that it is more than the variations within the groups. The sum of the variations between all individual groups and their mean divided by the sum of all the within groups variations should be positive. This will produce the F for ANOVA. And if we take this F and find out whether it is significant or not. How do we measure the variations? Not by the standard deviation, not even by the variance. We measure it by the sum of the squares. Sum of the squares is something, to obtain the variance, you find out the sum of the squares as the numerator. This is what we look for, the sum of the squares. That is to say, the difference between each reading or each dot and the mean of the group squared, so that we don't have any positive and negative data. And the sum of the squares of the differences between the groups should be higher significantly than the sum of the squares of the variations within the group. So now we'll see the ANOVA test in action. We are running a study to see if the grade of the severity of a certain disease, graded from 1 to 4, would influence the duration to recovery. So we have 4 different groups here with grade 1, grade 2, grade 3, and grade 4 with different durations for recovery. We have the mean for recovery of each. We first run the Levene's test to see if the data variances are much different or not, and it's not significant. Because of that, we can carry out the ANOVA test, and it would measure first the sum of the squares between the groups, the sum of the squares between each individual group, and the absolute mean of the 4. And the sum of the squares between the groups is this, and the sum of the squares within the groups, that is to say between each dot here and its mean, added the 4 together, will be this figure. Now, to degrees of freedom, we would need to divide the sum of squares with the degrees of freedom in order to obtain the mean square. The degrees of freedom for the between groups is simply number of the groups minus 1, so it is 3. And the degrees of freedom for within the group is the total number of patients, 30, minus the number of the groups, 4, so it's 26. When we divide the sum of the squares by the degrees of freedom, we obtain these two figures. We divide the between groups sum of square by the within group sum of squares, and it will produce the F of the ANOVA, which is 12 something, and that's highly significant. And we'll take another example to enforce how the ANOVA actually works, and to introduce two other small things. Now, this study is the variations in the safety margin of the pleomorphic adenomas depending on the type of the operation. So we have 4 different operations: the hemisuperficial, the recurrent parotoidectomy, the superficial, and the total parotoidectomy. And as you would expect with the hemi, it has the largest safety margin because this would be the smallest possible tumor. With the recurrent, you have a very narrow safety margin. With the superficial, you have a fairly sizable margin, but with the total done for bigger tumors in the deep lobe, you have all again very narrow margin. And you could see it in here: big margin for the hemis and for the semi and for the superficial parotoidectomy, and much smaller for the other 2 operations, and here are the data. Now, when we run the ANOVA test, because these are more than 3 different groups, it gives us the sum of the squares of the operation, which is this 3,700. Now, the residuals here are the within the group variations. It's sometimes called residuals, and that's 2,400. And now to the degrees of freedom, we have 4 groups here, n-1 equal 3, and for this we have 182 patients minus the number of the groups, 4, so we have 178 as the degrees of freedom. So we divide the sum of the squares between the groups with 3 and produces this number, and within the group by 178, and it produces a much smaller number. And the F, the statistic for the ANOVA, is quite high, and as you can see, it is very significant. Now, to the other 2 things I want to introduce here, this is the eta square, which is the effect size of the safety of the type of the operation on the safety margin, and it is almost 60% here, which tells you that 60% of the safety margin can be determined by the type of the operation. The other point is the post hoc tests. We know that these 4 groups are different, but which is different from the others, or which we run 6 different t-tests. The first group here will be run against the other 3, the second will be run against the other 2, and the third against the final one. So that's 6 different t-tests. These are called the post hoc tests. And as you can see, 2 of these were not significant. All the others were significant. The reason that we have 3 different columns here is, if you remember, the correcting the p-value for multiple testing. We are applying here the 3 different ways of correcting the p-value for multiple testing to obtain a more realistic figures, because we have run the t-test 6 times on the same study. There is a non-parametric test that can be used to compare the variations between 3 or more groups. If the ANOVA test cannot be used and the distribution is not parametric, then you can use the non-parametric equivalent of the ANOVA, which is called Kruskal-Wallis test. It works on the same principle of the ANOVA test, that the variations between the groups should be more than the variations within the groups. But to measure the variations here, we measure the sum of the ranks rather than the actual figures, rather than the squares of the differences, we actually rank all the values, and we compare the between group rank sums to the total rank sum to obtain the test statistic and find out whether it is significant or not significant. Correlation is used to analyze the relationship between two variables to see if these two variables are associated or not, and quantify the degree of association. For example, if you want to see whether two factors like tumor size in pleomorphic adenomas and the safety margin, you would expect that as the tumor size increases, the safety margin would decrease. So there is an association between the two factors, but the association is actually negative. When this factor increases, the other decreases. So this is, and the association can be a straight line, can be marked with a straight line or almost a straight line. So this is a measure of correlation. The other example here is, say, again, for example, association between the tumor size here and the length of the operation. You would expect as the tumor size increases, the operation would take longer time. So every time the tumor size increases a bit, the duration of the surgery would increase. So there is a linear relationship that can be quantified. Sometimes the relationship cannot be quantified by, exemplified by a straight line. It takes the form of a curve. It then would fall into another correlation category. You use other tests to describe this. We are here dealing with the linear relationship, the simpler form of association. And sometimes you cannot find any association between the two variables. And sometimes when this increases, this may decrease or may increase. Just a scatter of different plots here that you cannot draw a straight line for. So there is no association here. There is a curved line association here. There is a positive association here, and there is a negative association here. So this is an example of correlation between tumor size and a safety margin, and tumor size would be plotted in here and the safety margin in here. And as you see, as the tumor size increases, you would expect to have a narrower safety margin. So it's almost a straight line. You have all these dots marking the different tumor sizes against different safety margins. You can imagine a straight line passing quite close to most of the dots. So there is a negative relationship between, a negative association between the two. As one increases, the other decreases. Except that, of course, at the end, when it's too big, when the safety margin is almost zero, there is the straight line does not hold here. You could see this bit. And then you want to quantify this association, because not all the dots are exactly in the same line. Some of them are quite distant. We measure all the distances between these dots and the square and the straight line, and this would give us the Pearson R's, and the association coefficient here, the correlation coefficient, is negative, because as one increases, the other decreases, and it's 0.7. If it's perfect, the association is perfect, it should be a 1. The further away from the 1, the weaker the association. You could use another coefficient for correlation. This is the Spearman's rule, which can be employed in non-parametric data, and again it showed a correlation between the two, a negative correlation, but this time it's 0.8, and both are quite significant. It's important to note that we should not only concentrate on the coefficient of correlation, we should also check the charts. These are 4 different examples of 4 different associations, all with the same coefficient of correlation, or 0.816. This is quite high, but not perfect. Perfect correlation would be when it is 1. You could see here a scatter of the plots, but you could see that you can have a straight line somewhere in between in this curve. In here it's almost perfectly straight until the very end when it deviates, but you still get the same coefficient of correlation for this. Here you could have a perfect straight line but a very obvious outlier, so this is why this straight line correlation is not 1. It drops to 0.8 because of this outlier. And here you could see that the plot is formed basically of several dots at the beginning who are just forming a straight line vertically, which means that as this factor increases, the other remains the same. So there's hardly much relationship, but because of this outlier, it got the 0.8. So remember that the coefficient of correlation is important, but you need to check the curve because you can have different forms of curves for the same coefficient. The other thing to note when you are examining correlation is that the association holds only between the two limits of the sample you have. Here we are assessing the effect of age on the degree, on the duration of recovery from a certain operation. Now you could see that as the age increases, it takes longer to recover. So there is a relationship that you can imagine a straight line here somewhere. With increasing age, you have increasing duration of recovery, but that holds only between these limits, between the age of almost 20 and the age of almost 80. It doesn't tell you anything about the recovery duration in patients who are less than 20 years. You should not just assume that they would have less duration for recovery. What you should be confident of is only the limits of the test that you have run. And finally, there is a correlation test that can be used if the data are not normally distributed, if you have a non-parametric version for the correlation coefficient. This is the Spearman rank correlation coefficient. You use it if the data are non-parametric, if you have several outlying points, or if the data are not continuous, they are quantitative discrete, like IQ score, for example. You have 120, 121, 140, but you don't have 120 point something. So this is quantitative discrete, or the ASA score, again, is ordered categorical, but not absolutely continuous. In these situations, you use the Spearman rank correlation rather than the Pearson correlation coefficient. By this, we end this presentation on 7 common statistical tests. Assalamu alaikum.